Okay, as promised, the solutions and colloids section. So we have some of this is going to be important when we start talking about equilibrium, but not too much. So we talked a little bit about solutions when we were talking about liquids, but let's talk about what a solution is. So a solution, we've already identified it as a homogeneous or homogeneous, depending on how you want to say it, a homogeneous mixture of two or more pure substances. Remember, pure substances are going to be elements or compounds. Those count as pure substances. So how do you create a solution of salt water? Okay, so we have two things here that we need to consider. We've already kind of talked about this, so you should recognize these terms, but how do you create a solution of salt water? All right, so the solute is the substance in lesser quantity. I don't know what I'm spelling here. Substance in lesser, by the way, substances, substances, and lesser quantity. So in this, there can be more than one for this. And so in our example here, salt. Salt, again, any salt being sodium chloride in this case, but any salt, So salt is my solute. The solvent is the substance in greatest quantity. And there can only be one of these. There's only one solvent. It's the thing that does the dissolving, or it's the thing that's in greater quantity. In our example here of salt water, it is the water. Easy enough. Solutions can come in many forms. We're not just limited to the solutions, aqueous solutions. We can also have gases, like air, for example, is a solution. So we have to recognize that as well. All right, so considerations when we're thinking about the idea of what a solution is. So first of all, energy changes. When we have the formation of a solution, it seems like an easy thing. I take some salt, I throw it into water, boom, we have the formation of salt water. But the question is, why does that happen? Why does the salt dissolve? Why does a solution form, right? Are there things that we have to take into account? So energy changes that we need to think about are the cohesive versus the adhesive forces. And this is a good example of why we have to consider this, the cohesive versus adhesive forces. So if I have a positive and negative ion of our salt, we know that that interaction right there, that ionic bond is very strong. And as it turns out, this is the cohesive force, the thing holding the ions together or holding that substance together. And then we have the water molecule, so hydrogen as our example, which is going to interact with the negative ion because the hydrogen is positive in this example. And this right here is going to be the adhesive forces. So the problem here is salt, technically from an energy standpoint, should not dissolve because the cohesive forces are actually very strong. Ionic bonds, this bond is much stronger than the adhesive forces. So we would think that this would win and the salt would stay together and the water wouldn't be able to pull it out, pull it into solution. Okay, so again, in this case, what we have are the solute, in this case, the salt is going to be, so the solute interacting with solute is going to be our cohesive forces. And the solute interaction with the solvent are going to be the adhesive forces. Okay, all So for all intents and purposes, the energy should say that the ions should stay together because that's a stronger interaction than the water with the ion. But the other consideration that we have to have is something that we call entropy. Nature likes randomness. Nothing wants to stay in a solid form. It would rather be gas or some kind of mixture that is not well formed. Okay, so entropy is talking about the randomness of heat, the randomness of nature. So we typically think of this as randomness of heat, but really what it is the distribution of energy. Both of those things could be thought of as entropy. The more well distributed something is, the more dispersed energy is, the happier nature is. It wants to, it wants to turn everything into a vacuum or turn everything into heat energy. So we are going to get to entropy eventually, but what I really want to say about it is how this works until we get to the thermodynamics. Entropy is always increasing. Nature is always moving towards some kind of randomness. It always wants to disperse energy better. So what this is telling us is if entropy were at play, if just energy were at play, endothermic reactions, endothermic reactions can only occur because of entropy increases. So as I was saying before, this bond is stronger than this bond. So the cohesive forces are stronger than the adhesive forces. So for all intents and purposes, this should stay together. But the difference is this is a solid. And because this is a solid and water is going to help dissolve it, the added bonus of entropy, the added bonus of a randomness means that we are going to be in this situation where nature is happy to allow the energy to be a little bit negative, or a little bit endothermic if it can go to a solution or more random in nature. So this plus, let's say, a beaker of water versus that beaker of water with a bunch of ions in it. Nature is going to prefer the situation where we have a bunch of well-dispersed energy. So it's a little bit of a hard concept to understand. So let's talk about how a solution actually forms in terms of the energetics of it, which is a little bit strange to consider, but here we go. So three processes are going to affect this. So first of all, how this proceeds is we have solute molecules, we have solvent molecules, and then, so we have solute molecules and solvent molecules. In order for those two to mix, we have to separate both of them. So step one is separating the solute molecules. Okay, so that is we'll call that delta H of solute. That energy that we're going to be breaking interactions. I need to convert it from a solid or just, a solid into parts, things that are pulled apart. So that's going to cost us energy. We're breaking interactions. Because we're breaking interactions, this is a positive delta H. This process is going to be endothermic. It's going to cost us energy to do that. Step two is I'm going to take those solvent molecules and I'm going to separate the solvent. And that's this delta H of solvent. And that is also going to be breaking bonds. That's going to cost us energy as well, also endothermic. So those two processes together cost us energy. We get energy back when we take both of those that we separated and add them together so they combine together. So we broke these bonds and then we put them together and we formed a bunch of bonds back. So when we mix these things together, by mixing them, both the solute and the solvent, we get that energy back. And because we are that delta H of mixing, let's say, we are creating a bunch of bonds because we're putting them together. That is an endothermic or an exothermic process because we are forming bonds, right? And ultimately the question is, if something will dissolve, those two things have, well, I'm sorry, this process has to be greater than those two, right? So if I want if I want these two things to work, if this is going to proceed spontaneously, I need the delta H of solute plus the delta H of solvent. So the cost of those two things has got to be less than the delta H of mixing. If this occurs, this is going to be an exothermic reaction, right? So the mixing is greater, that gives us a better return on energy. So Hess's law, remember what Hess's law said. Hess's law states that the sum, the total change, oh, I don't know what I was doing there. Total change equals the sum of all changes. So by mixing them together, or I'm sorry, not mixing them, what I should say is from separating the solute, separating the solvent, mixing them together, my delta H3, the solute and solvent is going to give us energy back. We have a net exothermic process. So this should work. We should be able to mix these because we get a positive exothermic reaction. However, and if we have the other situation where the delta H of solute plus the delta H of solvent is actually greater than the delta H of mixing, what we expect to see is that is going to be an endothermic process. That is not preferred. Nature doesn't want to do that. And so we would expect this to not mix. So if that were true, anytime we had an endothermic process, we would not get a reaction, right? We should not, that salt should not dissolve in the water because it's not giving us a positive return on energy. But the truth is, what ends up happening is entropy can overcome the small gap of energy. So the endothermic processes can happen because entropy increases. Right. So that is ultimately what we're seeing. Endothermic processes can occur because entropy increases. So that's it. That's the energetics of solution. Entropy and enthalpy are at play here, which is a little bit strange because we never really had to think about it before. But you do have to have that addition of entropy. We want, liquids. We want, gases, solids are really low entropy. So we want to kind of increase that entropy. And we're going to talk more about entropy and thermodynamics. But again, the idea is mixing can happen as long as we can overcome energy gaps with a bump in entropy. And so we'll move into electrolytes next. This will actually help quite a bit when we're talking about acids and bases.